I think we can get started. So welcome everyone to this week's Autonomy Talk. This week is a great pleasure to have with us Professor Zhao, who is an assistant professor at the George W. Woodruff School of Mechanical Engineering at Georgia Tech. Something about Ye, he received his PhD degree in mechanical engineering from the University of Texas at Austin. He then moved to Harvard, where he was a postdoctoral fellow at the Agile Robotics Lab. And now at Georgia Tech, he leads the Laboratory for Intelligent Decisions and Autonomous Robots. His research interest focuses on planning and decision-making algorithms in the context of highly dynamic and content-rich robots. The particular focus is in challenging locomotion and manipulation problems, where he wants to get formal guarantees on safety, robustness, and autonomy. Now, as you see from the bio, he received a number of awards, among which I mentioned the NSF Career and the ONR Young Investigator Program. And today is going to talk about safe legged locomotion and navigation, robust motion planning, and interactive decision-making. This is a very cool topic, and I'm eager to learn more about it, and therefore I give you the stage here.
All right. Thanks for the very nice intro, Jolie, and hello everyone. So I'm Zhao from Georgia Tech, and so first I think I would like to thank the organizers for organizing this wonderful kind of autonomy seminar series. And I think although we are kind of in this post-pandemic phase, like returning back to the normal, but I think this kind of seminar series is still a very important channel, like for people to kind of exchange ideas all over the world. And so really appreciate that. And so it's my really great pleasure to present today and talk about some of our recent ideas, especially on like the locomotion and the manipulation, navigation problems, and how to reason about safety and the robustness properties of this very complicated system, especially when they are deployed in complex environments. So I think I would like to motivate this presentation by showing these slides about humanoid robots. And I think as some of you already know, there's kind of already a very long historical trajectory for humanoid robots that can be traced back to last 50s or 60s. And there has been like a series of very impressive humanoid hardware developed over the past few decades. You name it, like from the Japanese HRP series, Honda Asimo, to the more recent like NASA Valkyrie robots and the well-known like Boston Dynamics Atlas robots. And there has been, I think although there are still a lot of fundamental and technological challenge in like a sensing, autonomy, or even behavior reasoning, but I think we're really experiencing a great era of gradually transforming these humanoid robots from science fiction to reality. And now we are at 2023. If you remember last year in the Tesla AI Day, Elon Musk, they released their first prototype of this Optimus humanoid robots. Although I want to say, this first prototyping robots is still kind of integrates a lot of existing approach, like for foot placement planning, whole body control, sensing perception, but it's still very impressive. They kind of built this robot from scratch within just 9 months. And hopefully with the continuous effort and dedication of Elon's team, they can really impress our society over the next few years with this more mature humanoid robots and behaviors in very complex environments. So I think many people in this room are probably seeing a lot of cool videos these days from either Boston Dynamics or Agilities. So as we can see here, these robots can really demonstrate very agile dynamic behaviors in the outdoor environments. But there still exist many fundamental challenges from either the theoretical or experimental levels. So first, as we know, the dynamics here are highly complex. So they are high dimensional, nonlinear, and underactuated. And a lot of practical issues exist in this real system, such as actuator dynamics, delays and friction, etc. And many manipulation and locomotion problems nowadays, I think, are still a little bit far away from the capabilities of being operated in cluttered environments, achieve like contact-rich behavior reliably, or even kind of getting close to the human level agility. And from the algorithm perspective, I think many existing approach nowadays still lack formal guarantees on robustness, autonomy, task variety, or even safety performance. So it's very important for us to propose like new algorithms such that these robots can respond to unforeseen events reliably and adapt to new environments in real time. So I direct the laboratory of for the intelligent decision and autonomous robot at Georgia Tech. We call it LiDAR group. And we have a large focus on robust task and motion planning, decision-making algorithms for this highly agile and dynamic robotic system, especially on like the locomotion and manipulation. And we are particularly interested in these contact-rich problems where you have this deformable, non-rigid contact or even patch contact problems, as well as heterogeneous robot teaming with this kind of hierarchical tasks, motion, or even mission level behavior reasoning, replanning, and to achieve robust capabilities. So from a very high level perspective, a fundamental problem we are interested in is what's planning and decision-making algorithms do this select or manipulation robots need to achieve agile, robust, safe, or even collaborative behaviors, especially through physical contact. So in today's talk, I'm going to particularly address two questions. One is about hierarchical task and motion planning structure, and the other one is about distributed trajectory optimization. So the first question is about how we can design this hierarchical TAMP architecture to better reason about robustness, safety, or people call failure recovery. And I think many times the formal guarantees such as safety and provable correctness is only reasons at a specific layer and really cannot guarantee it across different planning and control layers. So in this case, how can we design resilient and robust mechanism to enhance the overall safety and task success rates if we can not provide 100% safety or even prove it? And the second question is about the trajectory optimization. And I would like to talk about some distributed optimization work we have been focusing on these days. And it's about its capability and the limits in achieving this dynamic consensus, especially for large-scale nonlinear programming problems. So hopefully I can convince you these are the important questions to explore by the end of this talk and show some promising results we have achieved so far if they are not the best ones. All right, so I think as some of you already know, in this fields of dynamic electric locomotion, there has been a series of exciting planning and control frameworks has been proposed, for example, like optimization-based planning and control approach, whole body operational space control, hybrid zero dynamics, sequential composition, you name it. However, most of these locomotion frameworks have rarely investigated formal decision-making and task planning method, primarily due to the very difficult, challenging underlying complex locomotion dynamics at the lower level. And this formal decision-making and task planning problems method actually have great potentials in enabling long horizon tasks over diverse terrain, as well as very proactive interactions with complex environments or even humans. And so far, I want to say this method has been primarily explored for grounded mobile robots, aerial robots, and some manipulation problems, but largely underexplored for like the system. So over the past few years, my group has been putting significant effort in this direction, especially for dynamic locomotion problems. So first, I would like to highlight some of our TAMP work over the past few years. Since 2016, we start to look at this we call unified whole body locomotion and manipulation problem from the task and motion planning algorithm perspective. We formulate this whole body locomotion planning problem as a two-player game between the robots and the interactive environment. And here the environments could be adversarial. For example, you see in this simulation, there could be like terrain get crashed, or maybe human appears in the scene as an obstacle. And the goal here is to synthesize a winning strategy such that the robots can always win the game. Basically means successfully maneuver in this very constrained environment. And we employ this formal method called the linear temporal logic approach to synthesize reactive planners, especially to make decisions for the robot contact sequence. And really to achieve this dynamic maneuvering, a fundamental question is how to intelligently identify and compose these complex motions, right? And this motivates us to investigate this template-based agile locomotion method. Here we refer a lot to human motions, especially those seen in parkour and gymnastics. Then we extract the essential dynamics and model the abstracted behaviors. And in the field of dynamic locomotion, many groups actually use this reduced order model, or people call it simplified model, for planning and control. For example, you have like inverted pendulum model, hopping model, multi-counting model, etc. And our goal is to unify this template model using sequential composition approach, especially for planning. And it is very essential to understand how to intelligently switch among these different locomotion modes in response to complex environmental events. Along another direction of research, we have been exploring this temporal logic-based formal method for especially navigations from multiple angles, including navigation in complex environments, safe learning and planning, being aware of environmental uncertainties, as well as heterogeneous robot teaming and task allocation and reallocation. So I will talk about some of these works in details later. All right, so first, let's start with a very specific locomotion problem, especially on push recovery, and think about how to design agile and robust motions using this task motion planning framework, right? And here I want to use this example to motivate some discussions about the design principles of this robust hierarchical planning framework. So for this push recovery problem, there has been a kind of long-standing like literature in this, especially in the dynamic locomotion community. There has been many related work such as the capture points, divergent components of motion, or MPC-based type of foot placement planning with different recovery strategies. However, many times the perturbation in these scenarios are just applied in a very simple and empirical way, and a systematic characterization of the perturbation applied phases, directions, and magnitudes, and deep analysis of this perturbation effect on the dynamic locomotion stability and behaviors is significant to design this practically useful recovery strategy, but they are largely underexplored. And also here, the leg crossing behavior actually has been largely ignored due to these potential self-collisions between two legs. So motivated by these challenges, we study how to design safe locomotion plans that are resilient to perturbations that can happen at any time. And I want to say this leg crossing behavior is necessary not only for the push recovery case shown on the top left, but also it can happen during certain like type of terrain locomotions. For example, think about a human walk over like a river, and there's kind of this zigzag stepping stones, and it has to use these leg crossing behaviors for successful maneuvering. And to avoid this leg collision, you can think we can encode them as the leg self collision avoidance constraints, which going to require us to solve this full body trajectory optimization problems. But before that, if you think about this push recovery problem from a very, very high level perspective, I think one of the most important thing for this selector system is to make correct foot placement decisions, right? And to achieve this, we use our reduced order model-based planning method called phase-based planner. So basically design the robot foot locations and the center of mass apex velocity in the robot center of mass state space. And in addition to that, our approach designed these so-called remaining cells to quantify these robust regions in this center of mass state space. And these remaining cells are computed analytically using the locomotion manifold, which actually have very nice closed form solutions, and we can compute it in real time. And then we use this temporologic-based method, which I'm going to show next slides, to sequentially compose and build dynamic transitions across keyframe states across multiple walking steps with this robustness notion. I would like to spend maybe just one single slide to share some basic ideas about linear temporal logic. And I think some of you might know, some of might not, but you can literally think about linear temporal logic as a formal symbolic language of rules and symbolisms to represent and reason about propositions quantified in terms of like linear time. And in this study, we use LTL to design the task specifications and synthesize robot decisions in response to environmental actions. And you can think this is a basic two-player game between the robots and the environments where they play a turn-based chess game. So these LTL specifications can encode a variety of desired safety, liveness tasks as you want. So for example, the specifications on the upper left can be interpreted as it is always true that when your keyframe state K is not in the steady state keyframe state region, then the next, so this circle operator represent next, so next keyframe state is going to recover back to the steady state keyframe, or the next keyframe state is going to recover back. So, and this square operator on the front represent it always. So this is basically represents a locomotion recovery specification. Say I want, if there's a perturbation, push my keyframe states out of the steady state region, I'm going to recover within 2 steps. And this is a kind of a well-received specification people want to achieve for like the system in this locomotion community. And this is just one example. So you can follow the LTL syntax and semantics to specify a series of goals or tasks you want the robot to achieve. And then we send these specifications to the off-the-shelf solvers for this offline synthesis. And then we can have these keyframe decision makers, and we can deploy it online, like detect the current online keyframe states in these robust remaining cells and determine what is the future actions plans. And here I want to say this automata, this G decision maker is actually a very large size. So it can have like a few hundreds nodes, a few thousand transitions. So this is definitely not a manual process. And this off-the-shelf synthesis tools can provide us like very formal guarantees on the correctness, etc. So then we embed this LTL automata into this hierarchically integrated TAMP framework as a higher level decision maker. And we symbolically represent the environmental perturbations exerted from this treadmill and treat it as a second player in this reactive game. And here the perturbation from the treadmill try to falsify the robot decisions. And you can think the high level temporal logic based formal method synthesize robot decisions to make sure that the robot can always recover from these perturbations through making correct foot locations and design the appropriate center of mass apex velocity. But here's one question. This LTL decisions is only made at the discrete apex keyframe state, right? When the center of mass is exactly on top of your foot locations. And then you may ask, how can we like handle perturbations that can happen at any continuous time, right? That's not necessarily occur at the apex state. So to achieve this, we design another middle level behavior tree execution layer, which can incorporate handle this kind of continuous perturbations and make local online modifications to your action sequence. And then this updated action plan is going to send to the low level trajectory optimization for full body motion planning. So overall, we have this hierarchically integrated task motion planning framework with multiple robust mechanism to address environmental uncertainties. And we evaluated this hierarchical planning algorithm on this carrying system, which actually mainly used for clinical and rehabilitation studies. You see there's a curved screen on the front, which can be used for virtual reality simulations. But for this study, we mainly stay on the mechanical side. And as you see here, the bird-tag treadmill on the dome can apply any directional perturbations at any specific time. And this is very nice platform for us to study this push recovery problem in a very systematic way. Here I show the case studies for 4 different directional perturbations. The 0-degree one involves leg crossing behaviors with around 4 to 8 centimeter in the cross-leg foot placements. We have systematically studied omnidirectional perturbations as well as those applied at different locomotion phases. So here, this spider chart shows the maximum tolerable perturbations. And this graph is actually asymmetric because of the very complex lag kinematics and dynamic constraints of the robots, especially in these leg crossing scenarios. So this work actually motivates us to think more about these robust strategies, right? And there are a few directions we are currently exploring, especially how to design more robust mechanisms by exploring these different system architecture properties when we have this hierarchical planning framework. And in certain scenarios, these high-level LTL commands actually cannot be successfully executed by the underlying full-body trajectory optimization because of the underlying complex physics constraints from the lector system. So in this case, we think we might leverage the feasibility of the trajectory optimization result to refine the task specifications and enable higher task success rates. And basically, you can think there's a bottom-up feedback mechanism, but we are still exploring how to formulate this problem in a nice way and with more principled fashion. And then at the temporologic level, I think exploring more advanced method that can reason about robust semantics or probabilistic satisfactions also give us the opportunity to quantify locomotion uncertainties in a more formal way. For example, there's this signal temporologic STL is very popular these days. But the question is how to scale this STL method to high dimensional system like the systems, because this STL approach oftentimes solve these mixed integer programs, which suffers the curse of dimensionality. And also, when we have a lot of task specifications we want to achieve, sometimes there could be some specifications that are self-contradictory, or certain specifications can really not be achieved due to the environmental constraints. So in this case, how we can leverage some like RL algorithms to find a kind of compromised solution. You can maybe satisfy the specifications as much as you can, but let's say if not all of them, and you have like kind of a relaxed solution. So this is another topic we are interested in these days. And also moving forward, we would like to incorporate this more like human-inspired locomotion strategies into our task specifications. And we have like kind of neighborhoods, labs working on the exoskeletons, human biomechanics. So we get a lot of inspirations from the how human recover from these external environmental perturbations. And I think this is going to be fundamentally important for the select system to navigate in the outdoor environments with this very austere terrains. Okay, cool. So next, I would like to maybe switch the gear towards especially the like the navigation problem and think about more complex environments. And here, a central problem we are interested in is how to design planning strategies such that the selected robots can locomote safely in partially known environments and at the same time achieve this complicated teaming task as we already saw in the autonomous mobile robots in warehouse. And there are multiple key considerations. First, this locomotion system needs to consider not only balancing safety, but also navigation safety. So for example, the robots should be able to avoid collisions with other obstacles or humans in the environment. And at the same time, it should plan its foot contact locations correctly and make sure it's balancing well. And another key component is the environment, which often involve rough terrain and partially observable features. And many times the robots only have a local field of view. In this situation, how are we going to parameterize and abstract the environments? Do we use fine or coarse abstractions? So all this is going to give us different computational workload and different planning capabilities. The last but not the least is the robots always want to collaborate with other robots, humans for collaborative tasks, like delivering a package or manipulate a bot together with other agents. To enable the safe locomotion in partially observable environments, at the low level, we design these locomotion gates using this phase-based planner, as I mentioned previously. And based on this reduced order walking model, we can design a set of locomotion safety criteria. So here, I won't go through all the mathematical details, but I want to give you just two quick examples about this safety criterion. So first, you can think if, let's say, given a fixed step length d, the apex velocity difference between these two consecutive walking steps is going to be bounded. And basically, you can think the robot cannot really change its apex velocity too much larger than a bound, which is a function of the step length. And another safety constraint is that the turning angle is actually bounded by the apex velocity, right? So this delta theta turning angle, you cannot make it too large if you are walking at a certain speed, right? Otherwise, it's a kind of very aggressive turning, you are likely going to fail. And basically, by encoding this low-level physical constraints into our higher level task specifications, right? These LTL specifications, we can guarantee that the high-level task specifications can be successfully implemented by the underlying locomotion planner or even the lower level controllers. And I want to say this is a fundamental difference between lagged robots navigation and the traditional grounded mobile robots or aerial robots. So here we have to think about how the underlying locomotion dynamics, the underlying models is going to constrain or maybe change the high level navigation decisions to maintain the overall task success rate. And given this overall, we again have another hierarchical planning framework composed of task and motion planning layers. At the higher level task planner, we aim for navigation safety, such as collision avoidance and other goal specifications, such as visiting location A infinitely often, or maybe collaborate with other robots. And this higher level task planner is composed of two sub-planners to handle task specifications at different abstraction levels. For example, the higher navigation sub-planner incorporates this safe navigation specification to design this global path and at like a course abstraction. And then within each course cell, there's going to be a finer level abstraction for the action action planner. And this action planner is actually incorporates the safe locomotion specifications and the design the waypoints for a few walking steps within this finer level abstraction. And then the middle level motion planner, we just talked about, is going to receive these commands from the higher level and design this local safe walking motions in the 3D and has the capability of maneuvering rough terrain and steering heading directions. So here's one question, right? And if you take a look at a close look at this navigation planner course level cells, you might realize that the robots sometimes might not perceive the obstacles because of the visual abstractions from the walls, which are actually represented by this red cell in the figure. So in this case, how can the robots make decisions on where to go next without full knowledge about the environments? And in this case, very natural, this direction is to reason about environmental observability. And to characterize this partially observable environments, we design a belief abstraction where we can use it to track feasible obstacle locations when this obstacles is out of the sight of the robots. And this abstraction is designed by partitioning the environment into multiple local belief regions. And then by dynamically tracking the obstacle status of these belief regions, we are able to track possible obstacle locations in these non-visible regions and further incorporate it into the robot's navigation decisions. With this belief tracking, we formulate this navigation problem again as a two-player game between the Cassie walking robots and the environments. And here, this environment has this mobile robots treated as one of the uncontrollable environmental actions. So here, the walking robots, Cassie is required to visit the pickup location at the upper level and move to the destination at the lower level infinitely often, while avoiding collisions with other obstacles, which is the other mobile robots in this case. And the belief abstraction of the environments is updated online based on the local field of view of the Cassie robots. And here you see the colored cell represents the dynamically changing belief region of possible obstacle locations, and the dark gray cells represent the non-visible regions that is going to be obstacle-free. We also implement this navigation algorithms on our digit robots. This is actually a successor of the previous, you saw like these Cassie robots, but both of them comes from agility robotics, and the lag kinematics and dynamics share a lot of similarities for these two robots, except that the digit has an ankle roll activation, which is actually very helpful for achieving this reliable turning behaviors. And here, the quadruped robots have their own task and are treated as dynamic obstacles. With the whole body passivity-based controller for digits, we can successfully achieve this navigation goals from the task and motion planning framework. And this is just a proof of concepts, and we are actually working on more complex environmental navigation scenarios where there could be maybe more aggressive obstacles, static obstacles, maybe blocking digits field of view, etc. So please stay tuned. Another direction of our lab these days is to explore even higher level planning problems. We call this scalable mission and task planning, especially for long horizon robotic tasks. So think about you have like a maybe robot manipulator start to sort objects into the box. And then after that, the walking robot is going to pick up the box and deliver this box to a destination downstairs. And this is a fairly complex planning problems due to the long horizon nature and this highly heterogeneous robot team in the scene. Some key research questions we are addressing these days is how to make correct contact decisions with the manipulated object and at the same time avoid collisions with the dynamic obstacles in the environment. So we are targeting both contact-rich and collision-free problems in this scenario. From the high-level mission planning perspective, we are looking at problems like how we can design decomposition algorithms such that this multi-agent system can be decomposed into multiple robot subsystems while guaranteeing the global task specification for the entire team. But there's fundamental challenging problems from the underlying dynamics of the walking robots, the contact problems for the manipulator. So this is, I think this is still a kind of open area I think we would like to explore in the near future. But I want to point out one limitation for a lot of temporal logic-based formal method. So this method often impose very strong assumptions on the allowable environmental events, which many times might not be consistent with the real physical world, right? And another topic along the same line is about this heterogeneous robot teaming of bipedal and aerial robots to resolve environmental conflict online that is not addressable by the traditional offline formal method synthesis. So for example, in this case, aerial robots is going to maneuver in this environment, and it might face a door blocking its path that is only detectable during the execution time. So in this case, this drone cannot really solve this problem, right? So it's going to ask assistance from the digit robot to open the door and then let the drone fly through this region, and then both system can kind of finish their remaining tasks. And to address this, we propose a high-level runtime replanning framework to detect such a situation and resolve the failure by resynthesis of other agents' motion decisions. And here again, this is kind of a proof of concept in the experiments. We are looking at small scenarios where we have highly heterogeneous robot teaming, even like have quadrupeds or even humans in the loop. And I want to say, really, to make this complex, like the system safely operates in our daily life, only designing reliable and robust motions is not really enough. And we have to understand the social context, because these robots need to frequently interact with humans. So the problem is that the social interaction is very complex because it depends on not only physics, right, but also a multitude of psychological or maybe sociological and other factors. And this makes reasoning and the learning problems incredibly challenging. Although I'm not an HRI person, but I know nowadays still a lot of HRI researchers still focus on how to design very specific interactions for very specific tasks or specific scenarios. So if we really envision these service robots that is able to collaborate very efficiently with our humans, this robot have to really learn how to interact in general with humans in a socially suitable fashion. And there are a lot of interesting topics, how to predict the human intentions, how to represent human knowledge and reasoning about it, and use maybe social cues and practice. And we would like to investigate these directions, especially in the context of like the navigation, like the locomotion. Okay, so I would like to maybe stop here for a second if there's any questions before moving forward.
Doesn't seem so,
No?
yeah.
All good. Okay, cool. I think we can continue and leave questions to the end. All right, so next I would like to talk about something different. Our lab have actually large focus on full body dynamics-based planning problem, especially trajectory optimization, and basically think about how can we decompose this holistic trajectory optimization problems into multiple sub-problems and then achieve dynamic consensus and talk about its capability and the limitations. So I would like to put this in the context of momentum-aware trajectory optimization, because the angular momentum is very important when these robots achieve very agile and dynamic motions. In the literature, there has been a large body of works using these so-called single rigid body models, or people propose extended version like a 3-body or maybe 5-body models with different level of model abstractions. And some other works even use this neural network to learn this time varying momentum inertias, etc. And on the other hand, there has been quite a few research labs kind of proposing this alternating direction method, basically decomposing the entire trajectory optimization problems into 2 or maybe more blocks and alternates between them to achieve dynamic consensus, which actually show great promise to solve more complex planning problem. However, I want to say there's still no alternating mechanism framework that can really handle both like a contact sequence optimization as well as being aware of both inertia aware centroidal momentum and whole body dynamics all at the same time. In this work, we propose an alternating method for the full body trajectory generation offline to achieve this dynamic consensus between centroidal and whole body dynamics. And then at the lower level, we have a convex MPC with the full centroidal dynamics for this online tracking. And this work is leads by my student Ziyi and Bruce from Hutchinson's lab. But in this talk, I'm going to mainly talk about the trajectory optimization part and discuss the distributed optimization structure design. In general, when we solve this large-scale constraint trajectory optimization involving both centroidal and whole body dynamics, there are usually a long list of equality, inequality constraints have to be dealt with. And take a look at this problem, right? How complex this formulation is and how many numerical problems it can probably induce from this holistic optimization perspective. And we certainly need to think about if there's any internal structure we can leverage in a principled way, or maybe decompose the problem into like a distributed fashion into these multi-blocks and solve it in a kind of distributed fashion, right? And this is our proposed alternating algorithm between the centroidal and Hobart optimization. And overall, the centroidal and Hobart optimization is solved alternatively until consensus. And here are some details in the centroidal optimization. Instead of solving this single rigid body model, we use a centroidal dynamics model with the so-called eco-momental ellipsoid parameterization, including the ellipsoid's size and orientation, which is denoted as the I ellip. And in this study, we add a cost term to let this I ellip track another moment of inertia term, ICRB. So this is the reference composite rigid body moment of inertia calculated from the Hobart optimization. And this cost is shown in this red box. So here, this eco-momental term basically means there's kind of equivalent ellipsoid that has the same moment of inertia to this composite rigid body moment of inertia ICRB. And the nice thing is that now these centroidal ellipsoids can get rid of the direct dependency on the full body joint states, right? So, but at the same time, it's sort of indirectly incorporates the full body information through tracking this ICRB. And you can think about this centroidal momentum ellipsoid is a more advanced and dynamics consistent version of the single rigid body model, but without any simplifications. And at the same time, we have an ellipsoid mass constraints to be enforced to make sure this robot mass is always going to remain the same. We can add additional constraints and solve this problem using the direct approach. And here we decide to use this IP-opt method. And then for the whole body optimization, we incorporate the full body dynamics model, but with minimal additional constraints. So we only have the joint torque limits and the friction constraints. So we really don't need to worry about the centroidal reference, centroidal momentum, and the foot location sequence, because all of these parameters are already offloaded to the centroidal momentum optimization. And here we solve this whole body optimization problems through the differential dynamic programming DDP, and we use Crocodile as the underlying solver. And then we evaluate this algorithm for both mini cheetah and A1 robots. Our method can generate highly dynamic locomotion gates, such as this cantering, as well as this long aerial phase for this dynamic parkour maneuvers. And this is actually a very interesting one to differentiate from the single rigid body model or the traditional centroidal momentum model, which heavily rely on the ground reaction forces. Here we study this zero gravity body reorientation problems, which is actually called inertia shaping. So you might saw the videos like the astronauts kind of do the self-rotation in the International Space Center. So this is kind of a similar scenarios. And because there's no gravity, all external contacts are present in this problem set. So the robot is forced to rely on its limb motions to produce this turning behavior. And the robots start with a static initial configuration, and the goal is to turn its trunk by 90 degrees in 2 seconds. And this is really unachievable by the traditional single rigid body or the centroidal momentum models, which, as I said, rely on the ground reaction forces. We also benchmark the performance of our approach with the single rigid body method plus this inverse kinematics as a baseline approach. Here we do this 180-degree spinning, and we see both methods can actually generate these trajectories pretty well, as shown in this simulation, in this visualization. But if we take a closer look at this scenario, we can see our alternating optimization algorithm actually leverage additional lag movements, especially during the takeoff phase, which leads to a larger angular momentum. And this larger angular momentum actually induce a very special motion, rotation motion at the very beginning phase during the takeoff phase, which actually play a key factor to successfully accomplish this task in hardware. And when we implement it on the real system, we're using exactly the same controller for both planning method, and the trajectory generated by the single rigid body model can really not achieve this full 180-degree rotation. And if you look at closer to the motions using our method, this robot have this initial swift counter rotation at the very beginning phase. And this is a small but non-trivial change of the angular momentum actually guarantee a high fidelity momentum trajectory to be tracked by the underlying controller and achieve this 180-degree turn. And I want to say this angular momentum change is completely solved by our trajectory optimization without any manual hand tuning. So this is kind of the beautiful part of using optimization-based planning approach to generate a highly dynamic and momentum consistent motions. We also have more hardware tests on the MPC controller, so I'm going to skip it. We also benchmark the consensus performance using our alternating method, and one kind of using a more traditional hierarchical architecture where the centroidal momentum module sends all the signals to the underlying whole body optimization in a single top-down direction, right? But our approach is kind of alternate across two blocks. And by examining the residuals for different reference tracking cases, such as a center of mass, end effector, angular momentum residuals, we can clearly see that our method actually outperformed than the hierarchical one in all cases. And I think the reason is kind of obvious because our method uses this alternating mechanism to achieve better consensus between the centroidal and whole body dynamics and give us more consistent results. Okay, so I think before closing this talk, I would like to maybe pose two questions and have some discussions here. So first, thinks this alternating direction method is promising for better consensus. So can we really generalize it to more complex problems, such as those involving physical contact? And the answer is partially yes. So recently we have some other works actually generalizing this alternating direction method to this real-time MPC for manipulation with deformable contact. I don't have time to talk about the details, but the key point is that we can have more blocks to handle not only the whole body dynamics, but also the physical contact models. But this is just the 7 degree of freedom robot manipulator, which is not as complex as humanoid robots. Well, although the deformable contact part induce some physical complexities. So what about more complex dynamics for like the system and even incorporating the contact physics, like people try to impose this linear complementary constraints, which are very difficult to solve. Or maybe you have like definitely have higher degrees of freedom robot dynamics. So how can we achieve dynamic consensus in a more efficient way? And currently, I think a lot of this alternating or this kind of distributed trajectorization method are still largely depends on, or maybe I want to say restricted by the numerical convergence performance. And there might be more fundamental problems we should look at from the optimization algorithm structure design perspective. For example, how should we divide the entire optimization problems into sub-problems in a principled way? What is the appropriate primal dual updating sequence? I think all of these questions certainly needs more investigations. So another question is about this angular coordinates. So what is the appropriate representation for the angular coordinates at the centroidal level, right? And this question seems not very related to the trajectory optimization architecture design, but actually it could be potentially make a difference, like especially think about how this centroidal optimization information is going to be processed in some blocks and pass it to another blocks. And so I think these are definitely related questions. So I don't have time. I think really there are a series of work exploring these directions in the humanoid community. People propose different angular representations like angular excursion, used a lot by Boston Dynamics, equimomental ellipsoids, and there's also this recent minimal perturbation coordinate from HMC and POSAS lab. I think each representation have their pros and cons. And also, I think many existing locomotion tasks nowadays still aim to just try to minimize this centroidal momentum, right? Kind of have minimal angular coordinates variation. And this is, I think this is very unclear how this angular representation is going to work for when we have like highly agile bipedal locomotion behaviors such as running, flipping, and especially those involving large angular momentum variations using the arms and swing around. And this is just one step further. So we have some very preliminary results for this agile locomotion motions like jumping and flipping with the dynamic arm movements. And here you can see the legs and arms can definitely not negligible in these cases. And here we show, so the blue ellipsoid denoted the equimomental representation, while the yellow one denotes the angular excursion representation. And in our initial observations, so we noticed that this equimomental ellipsoid is more aligned with the torso orientation, while these angular excursion ellipsoids move to kind of different configuration that has less physical intuitions at the end of the motion. So we really don't have a clear answer yet, but I think we are interested in understanding what is the physical interpretation of these different angular representations and what is the best way to handle these very agile motions with angular momentum representation. So at the end, I just want to give a highlight. This is kind of a new direction along the locomotion and manipulation. We are designing this new sensing-rich bipedal robot Infandar with the third soft superlimb arm. So basically equip this high-resolution tactile sensors and morphologically reconfigurable robot foot. This new humanoid robot is essentially going to enable very high-resolution context sensing capabilities for locomotion and manipulation or even navigation. And we would like to explore this TAMP problem, trajectory optimization problems I presented already with the context-rich sensing in the loop. So I think I would like to maybe close my talk at this video. I think as time goes, we're really marching towards the goal of deploying a team of robotic system in our daily life, and hopefully over the next 5 to 10 years, we are going to see more humanoid robots serving our society better, like help us carry the heavy payloads, entertainment, and really changing the way we live and work. And with that, I'm going to stop, and I would like to thank my students, my collaborators, and the funding agencies. Thank you.
Thank you, Ye, for the great talk. Let's open the stage for questions. You can either write your question on the chat, and I will repeat it for you, or you can simply unmute yourself. So we already have a question in the chat. Maybe I'll break ice with that one. Or Emilio, do you want to start?
We can go with the question.
Let's go with the chat one. Okay. So Nahid says, greetings, professor. Thank you for a great talk. How can we compensate the model error for underactuated bipeds since we are using reduced order model like inverted pendulum?
Yeah, that's a great question. Actually, there has been kind of a long conversation in the locomotion community about what is the right model we should use, right? And there are pros and cons of using the reduced order model versus the full body dynamics model. And I want to say it depends on what is your focus. And I think if you're really looking at using this like the system to navigate in complex environments, well, I think based on what we have right now, I think reduced order model is probably more appropriate from the computational workload aspect. But if you just kind of focus on designing the local behaviors, like walking over some rough terrain over the next few steps, the underlying control and full body trajectory optimization, you definitely, I think the kind of full body model is more appropriate. And yeah, I mean, as to the compensation for the model errors, yeah, I think we kind of realize this problem because many times there are a lot of low level like dynamics are kind of ignored by the reduced order model, but this actually can cause failures. Whatever the high level like formal guarantees you can provide at the task level, at the decision-making level, you have to, when you employ this in the real system, there are often going to be failures because of, well, not only model errors, but also environmental uncertainties. So our strategy is really, I mean, we don't have like kind of like a formal guarantee or formal theorems when we look at this hierarchical planning and control framework. But what we are trying to do is we propose multiple mechanisms to compensate the errors, and using like replanning and kind of feedback, not only the top-down like structured communication, right? Also bottom-up, and then it's kind of like from the system design perspective to handle all different kind of failures and model errors. And we are still also curious if there's kind of a theory which can really give you the formal guarantee for this entire hierarchical planning framework, but we don't have a clear answer at this moment. Although we have like kind of formal guarantees at the specific layers, right? At the higher temporal logic task planning layer and the motion planning layer, we have this robust region design. But when we cross different layers, it's definitely a hard problem. Yeah. I hope this answers your question.
There is a follow-up, actually. Thank you for the great insight. Can we consider the lag navigation problem for under-actuated chassis robot as a partially observable macro decision problem?
Yes, definitely. I mean, right now we kind of more exploring this task planning problem as using this deterministic framework, but you can definitely induce like kind of the probabilistic version to parameterize your robot models, to parameterize your environments, and yeah, definitely. I think this is actually some directions we are exploring these days. Yes.
Okay. So there are other questions in the chat, but maybe let's alternate a bit. Let's go maybe for a question from the live audience. Anyone wanting to ask something?
Well, I can take an opportunity. Now I jump at it.
Go.
You know, first of all, you know, I really like your talk, and I was especially impressed by the video of the robot cat or dog. I like to think of it at you know, like reorienting itself in zero gravity. Made me think of you know, when will you be able to throw your robot up in the air and make it land on its feet?
Yes. Sorry, can you repeat your question? Like landing this robot and still testing.
Yeah, you know, like a cat, right? So you know that cat always, you know, are able to land on their feet, right? So this really reminded me of that, right? So
yes, and
take your robot also, and throw it up in the air.
Yes, this cat, and also I think other animals like a lizard, and when you throw them from the air, they can they have really kind of, I think, super like powerful like brain to processing this and make sure when it's landing, it's going to reorient its bodies and to make sure it's landing successfully. Yes, this is something we actually tried once in the lab, but actually we broke the leg because there's definitely like a kind of actuation limits from the lower level. But that could be a good example to validate the whole framework, right? This kind of reorientation. So right now we just reorient. Well, it's kind of just reoriented around the yaw direction. But if there's kind of more aggressive motion, we can really, I think that's a really good example to testing this, we call the angular momentum trajectory optimization.
Right, because, you know, this is a classical kind of example of when people talk about non-autonomy, for example, right? So that is a typical example, right? The cat that by just doing internal motions can reorient itself, right?
Yeah.
If you can do a practical demo, it would be awesome. I mean, maybe even in simulation, right? So where you where you can see that without breaking legs or something like that.
Yes, yes,
I would love to see it.
Yeah, we got the mini cheetah recently, and I think that's maybe a more reliable platform. We can try this type of task. But previously, when we try on this is a different robots from Unitree, it actually failed. And I think I know some USC researchers. They actually do the kind of flipping motion and like landing from like a box at 2 meter height, and then they can kind of landing success. But they are testing, I think, different control or planning algorithms. Yeah, but I think that's a really good example. We should really try out and really think about the powerfulness of the algorithm we are proposing here. Yeah, that's a good point. I will talk to my students later.
I would love to see it.
Yep.
Now, what is the role? Do you use any pre-computed gates in your optimization, or what is the role? What do you think is the role of some pre-computed or?
Yes, definitely. This cantering motion, actually we use some kind of mocap data generated from some like open source data sites. But in general, this algorithm can be, it doesn't need to depend on like a predefined context sequence. So actually the one of the kind of the specialty of our algorithm is that solving this optimization, we can solve the context sequence. So the context sequence is part of the decision variables of our optimization. There is kind of a literature in this area. People call this context implicit trade-off or context invariance. And this is sort of the way, but definitely if you have data, you have expert demonstration, that would definitely help the optimization to get the convergence. So yes.
Okay.
Yeah.
And then, it's a little bit of a clarification. When you have your game theoretic approach, what are the actions for your adversary, right? So was it that
the temporal
place random obstacles in your path, or
in the navigation problem for the game part? Go back. Yeah, so it depends on the problem. Like for example, for this type of environmental navigation, the actions is going to be the contact locations and the apex the states. So this kind of center of mass apex states. But for the yeah, I mean, in this case we use the reduced order model, so it's kind of like a set of key parameters parameterized in this lower dimensional space of the robots. That's the actions we use for this model. But you can definitely design other, I mean, depends on the tasks. If you have like more complex manipulation problems, you can have other type of representations for your contact sequence. We haven't really incorporated the kind of the parameters related to dynamics into these decision-making problems, like forces. But I think we are trying to kind of abstract the behaviors, the high-level behaviors, mainly from the kinematics or geometric aspect. But there might be more interesting stuff, like whether we can incorporate the contact forces or any other kind of frictional contact properties into the high-level decisions. But that's something we have not explored at this moment.
Okay, thank you. Yeah, I don't know if other people have questions.
Yeah, thank you for the questions, Andrew.
Yeah, thank you for the questions. There are other couple of questions in the chat. First one from Vikyat. I think it's a follow-up with this cooperation part of things. In particular, the question is, are the tasks in the cooperative tasks, are the tasks predefined for the humanoid, quadcopter, or human in the loop? So this before execution, or are they actually arising at runtime where entities collaborate based on dynamic limitations?
Yeah, that's a good question. Yes, there's a, let me go to this slide. There is a, I think he's asking this one. Yes. So yeah, there's kind of offline generated nominal paths of the action sequence for both robots. But the problem here we are trying to address is that sometimes the assumption you made for the environment could be wrong. So there could be like a runtime, like kind of emergencies or new environmental actions shows up. And in this case, how you can kind of do the runtime modifications, right? The runtime replanning to guarantee you can still accomplish the task. So this is what's the main like kind of topic for this work. But yes, we do have like kind of a nominal path action sequence we want the robots to accomplish in the nominal environments, but we are considering the kind of emergency environments in this study.
Okay, thank you. And there is another question, which is, can a model-free controller be combined with symbolic planning and distributed optimization methods to enhance the robustness and safety of like the locomotion? This is a more general question, I think.
Yeah, that's a good question. I think when you say model-free controller, I assume you refer to the like kind of learning-based approach. Yeah, I mean, we sort of like thinking about this problem, right, from the symbolic planning aspect. Many times these specifications are designed by human users. And if it's just a few specifications, that's might be okay, and there won't be any conflict. But when you really have like many specifications, especially for a team of robots, there could be some like a self-contradictory specifications, right? Even the human designer cannot be aware of. And in this case, how this like learning algorithm can really learn a kind of a relaxed version, right? So you are trying to maximize your satisfaction for the specifications, but there might be still some violations can be not avoided. And I think these are the powerfulness of this learning-based approach. I think we would like to explore. And for the trajectory, this distributed optimization method, yeah, I mean, there are tons of, I think, existing literature combining try jobs with like learning approach. And well, usually many times people solve this trajectory optimization offline because it's model-based, and it's kind of more reliable, and it's very good for your like sampling efficiency, the convergence of your RL algorithm. So I think overall having like this kind of model-based approach, I mean, from the traditional optimization can help improve the kind of well, I'm not sure robustness, but like more like the kind of sampling efficiency and convergence. Or you can encode like a safety into your model-based approach, but it's also kind of indirectly reflected in your RL algorithm. Yeah, definitely. I think this is a good direction. We have not explored it yet, but I think this is kind of promising direction to look at.
Great, thank you very much. And there is a final question, which is, can we utilize notions of H-infinity methods for the consideration of both external disturbance and model error?
Yes, so definitely, but we haven't put this into the kind of classical robust control formulations, and but definitely, I mean, you can kind of like solving this H-infinity norms of the perturbations as you want. There's kind of a lot of tight connection between this optimal control and the robust control, right? But it's sort of something, yeah, I think we're more from the numerical, exploring the problem from the numerical optimization, and we have different ways to quantify robustness. Like I didn't talk about the work in this talk, but we kind of think about design robust cost functions to handle the contact. So we have frictional contacts, like either in the distance or friction coefficients, how you can design a robust cost function in your trajectory optimization and handle these contact modeling errors. And it's a little bit different literature, but I assume you have the corresponding ways in the kind of more classical robust control formulation. Yeah.
Great. Thank you very much, Ye, for the great talk and also this great discussion. I think if you have other questions, you can follow up with Ye privately, and probably there will be room for that. By this, I want to thank you again, and good luck for all the next projects and adventures. It's been a pleasure.
Thank you. Thank you all.
Great. And see you all next week for the next Autonomy Talk. Bye.
Bye-bye.